Hey everyone, welcome to the first video for section 5.4. So we're jumping ahead to 5.4 just to hit this section real quick because it's a short little section and it's nice to fit it in here before we start delving into stuff that'll take a lot longer so we can do a break now for the exam. So section 5.4, the first part we're talking about is talking about Euler equations. So this is a second order linear ODE. It's not constant coefficient, but it has an easy way to find the solution. So we're going to look at this ODE, how you find solutions to it, and start going through the different sort of cases again, because it's going to give us another quadratic polynomial. So we have three different cases for the roots again: real and distinct, complex conjugates, or repeated roots. We'll go through all three of those cases for the section and show you these kind of equations and how you can solve them. Let's go ahead and jump on into that. So in this section, we're talking about Euler equations. Now what these are ODEs of the following form. L of y, so L is going to be our operator here again, is going to be x squared y double prime plus alpha x y prime plus beta y equals 0. So we're solving the homogeneous case here. And here we need to have that x is positive. So in this case, we obviously need to avoid x equals 0 because at x equals 0, our p and our q are discontinuous because in this case we have our p of x is going to be alpha divided by x and q of x is beta over x squared. So these are discontinuous at 0. So just for convenience sake, we're going to say we're going to stay on the positive side of 0. So we're taking x bigger than 0 for this problem. Now, when we had constant coefficient equations, we guessed e to the rt is our solution. And why did this work out so well for us? Well, this worked out really well because our equation was a y double prime plus b y prime plus c y equals 0. And if you plug in e to the rt, taking derivatives of that just brings down constants and leaves it as e to the rt. Now what this ends up giving is that when we do all of this calculation, we end up with a r squared e to the rt plus b r e to the rt plus c e to the rt equals 0. And what happened is we ended up with an e to the rt on every term, so we were able to cancel it out and get down to just a quadratic polynomial. Now, for the Euler equations, we're going to also guess a form of a solution, but it's not going to be the same one. So here's our equation here. And it turns out for the Euler equation, we want to guess y of x equals x to the r for our solution. So instead of e to the rt, we want x to the r. Now why does this make sense? Why is this going to work in the same way? Well, if you think about it, when you take two derivatives of x to the r, what happens? You pull down some constants and your function becomes x to the r minus 2. For one derivative, you get x to the r minus 1, and then the y stays constant. So if you look at our equation up above, what we're going to end up with is this first term is going to have an x to the r in it, because it's going to have an x to the r minus 2 from the y double prime, and then the x squared puts us back up to x to the r. Same thing for the next term, and then for the last term, we're going to have an x to the r in each term, which we're going to be able to cancel. So just like last time, the function part's going to cancel out, and we're going to be left with a polynomial. So now let's go ahead and try to find this polynomial. So we'll start with our equation again. X squared y double prime plus alpha x y prime plus beta y equals 0. And we're going to assume that y is x to the r, which means y prime is r x to the r minus 1, and y double prime is r minus 1 x to the r minus 2. And then we can plug that in. So if we plug all of these in, we get a x squared times r minus 1 x to the r minus 2 plus an alpha x r x to the r minus 1 plus a beta x to the r, which we can simplify to an r times r minus 1 plus alpha r plus beta all times x to the r. And that's what we wanted to see, right? We wanted to see that we had the same thing on every term. We have an x to the r on the last one, the middle, and the first all have an x to the r in them. And I want this to be 0. So now I can divide both sides by x to the r. Remember, x is bigger than 0, so I can just divide both sides by that. And by expanding out this polynomial a little bit, I get that I have an r squared. I have plus alpha minus 1 r plus beta equals 0. So for Euler equations, this becomes our characteristic equation. And again, we're going to get two roots of this polynomial. The roots are of the following form, just by using the quadratic formula. And now, as before we talked about in section 3.1, there are three cases for the roots of this. They are either real and distinct, they're repeated, or they are complex conjugates. So again, for this first video, we're just going to look at the real and distinct case. So assume alpha minus 1 squared minus 4 beta is strictly positive. So there are two real and distinct roots, R1 and R2. Then we want to say y of x equals c1 x to the r1 plus c2 x to the r2 is a general solution. What do we need for this? We need the Wronskian of our two generating solutions there, r x to the r1 and x to the r2. We need that Wronskian is 0. And what you can check, I'm not going to do all the calculations out here, but you can check that the Wronskian of x to the r1 and x to the r2 is r2 minus r1, x to the r2 plus r1 minus 1, which, since x again is positive and r1 is not r2, this is not 0. Which means we're in good shape. Our Wronskian is not 0, which means our general solution is of this form right here. So if you have two real and distinct roots, this gives you the general solution to your Euler equation. All right, that's the point for this video. I'll give you a problem where you're just supposed to solve this for a certain equation that I'm going to give you. So take a look at that. We'll put that in the sheet. I'll write that up for you here right now. All right, so there's one example for you guys to work out. Put that on the worksheet and then bring that into class tomorrow. In the next video, we're going to look at the other two cases where you have a repeated root and where you have complex valued roots. We haven't touched those yet for the constant coefficient case, so I'm going to be a little vague about how it works in this case, and then when we get to the actual cases in Chapter 3, Chapter 3.3, and Section 3.4, we'll hit them in more detail. Thanks a lot for watching, and I'll see you in the next one.